slow things down. So as everyone's been listening to us chattering back and forth for the last 10 minutes, we'll go ahead and get started. And it's my pleasure to welcome you to our first physical division seminar of the month. And as we announced last month, we are moving to, now that it's summer, most places, not here yet. We still have a month more of classes, but we're moving now to an every other week schedule. So the second and fourth Friday of the month. And we're using the summer to honor our Phys division awardees, as well as the JPC lectureship recipients. And we're going to start off with Emilie, who's giving the first of the 3 JPC lectureships. So I just want to welcome everyone on behalf of the organizing committee. Also thank Phys Tech, who has sponsored our Zoom account and our ability to be able to continue to run this. And I'm going to turn this over to the Deputy Editor of JPCC, Greg Hartland, who will continue on with the introductions. And I'll stop sharing the screen.
Well, hello, everyone. It's my pleasure to introduce Professor Emilie Ringe. Emilie did a PhD at Northwestern with Rick Van Dyne, looking at sears and single particle spectroscopy before taking a research fellow position at Cambridge. She moved to her first academic job at Rice, where she set up an electron microscopy experiment to study single particles, single metal particles. And in 2018, she returned to Cambridge, where she heads a very dynamic group that studies the properties of materials with optical and electron probes. Her work has led to a very number of high-profile publications in the spectroscopy of particularly metal particles. And because of this, she was awarded this year's JPCC Lectureship Award, which we hope is the first of many. So today she'll tell us about her work that she's done so far, and I hope everyone enjoys the seminar. I'm certainly looking forward to it.
Thank you. All right, can everyone see my screen and hear me? Yes, okay, I get thumbs up. This is brilliant. I don't want a pen, I want a laser pointer. Brilliant. Well, thanks so much for spending the next hour or so with me. What I want to do in this time is tell you about the really recent results we have focused on magnesium plasmonics. This is not really where I started with my academic career, but this is where I landed in the last couple of years, and we're really excited about the results we're having, and I hope that I can convey that excitement today with you. Okay, slides should advance, yes. So this is my group just pre-pandemic. We have established ourselves in Cambridge in 2018, and we've received so far significant funding from the ERC and EPSRC, which are the funding agencies of Europe and of the UK. And obviously, I don't do this work alone. My group is a very collaborative, dynamic group, and I want to thank them for all of their wonderful work. I also have a number of collaborators in the US and here in the UK, and there's 3 key collaborators right here. We do a whole bunch of stuff in my group, and before I start telling you about magnesium, I'd like to overview the other things we do. So if you have questions about that kind of stuff, well, then we can discuss a bit later. So we do develop quite a bit of hyperspectral tools for plasmonic structures. This basically makes our life easier by enabling us to acquire data and in much larger format and much quicker. When I was at Rice, we did a lot of 2D optoelectronics, basically just collaborating with what people did there, had a lot of fun with that. Continued a little bit in Cambridge. We also do quite a lot of outreach for individuals with visual disabilities. At Rice, we worked with a center for these individuals. And here in Cambridge, we work with the various Cambridge museums to put out exhibits that help make people understand that you don't always have to see to believe. But really, today I'm going to talk about our work on bimetallic and earth-abundant plasmonics. And the key here is that we humans are fascinated by color, right? Well, some people anyway, buy very expensive works of art. We put color in our food, we put color on our buildings, And we really, think about color as a decorative issue, but scientifically, color is really the way we interact with light, and this is how we can absorb photons, say in a photovoltaics, for instance. There's a number of ways to make color, so you can think about an organic dye having a transition in there. You can think about a transition metal center, for instance, having also transition. Or you can think of a band gap where you generate the onset of absorption and hence color. What I'm going to talk about today is none of these three. Is actually a completely different phenomenon, and which is intrinsically nanoscale. And this is called localized surface plasma on resonance. So imagine you have a nanoparticle of a metal, and this metal can be thought of as a stiff matrix of positive ions and a cloud of delocalized electron. You put an electric field next to this metal, well, the cloud of electron will polarize in response to that electric field, moving the center of charge away from the positive to the negative charge. If you release that electric field, then the electrons will swing back towards the center of charge, and there'll be a little bit of inertia, and then they'll move sort of back and forth. If instead of a single kick of an electric field, you actually send an oscillating electric field, i.e. light, well, then you can actually involve a resonance if that oscillation is at the correct frequency for that cloud of electron in this nanoparticle. This is what we call a localized surface plasma resonance. This gives rise to enhanced photon absorption and photon scattering, which can be seen in the far field, as well as an enhanced electromagnetic field around the particle, which we often refer to as the near field because it's localized near the particle. Basically, everything changes the near field and the far field properties of these particles. So different composition mean different LSPR, different size, different shape, different surrounding environment, and so on. And on one hand, this is great because it gives us a lot of knobs to turn. On the other hand, it's quite complicated because every single particle, ever so slightly different they might be, are going to have a different response. And so we have to do quite a lot of single particle spectroscopy to tease out this heterogeneity. We are very interested in these phenomena, not just because they create very colorful samples, but actually because they can localize those electric fields. And as my PhD advisor, Rick Van Duyn, has shown, this can lead to enhanced spectroscopy and sensing, which is really quite useful. And a bit more recently, people are increasingly interested in this idea of local energy dissipation. You excite a plasma, it decays. Well, what does it decay into? It can decay into non-thermally equilibrated electron-hole pairs. It can decay into heat. And that is also a localized energy phenomenon that can be transferred. So there's a lot of ways we can use these basically as a block to interact with light. To study them, we can look at them again in the far field or in the near field. So this is what we do when we want to look at them in the far field to see the absorption or the scattering. And simple thing to do, take a UV vis spectrum, right? Look at the color really. Or we can do single particle scattering. And this is just with a dark field microscope. Each of these dots is a diffraction limited spot, which we're going to go and take a spectrum of. So doing these kind of techniques, we get either for our UV vis, we get a bulk extension. So this is an ensemble average. Or on the right, if we do single particle scattering, well, then we get an information about the scattering from a single particle. And that can be correlated with a structural analysis, such as TEM, SEM, and so on, and really teasing out beyond the bulk averaging. There's other ways to do this and to probe the particles in the near field, and that's what we've been doing really a lot of in my group, and is to look at electron energy loss spectroscopy. And this is in a TEM, okay, where you're basically going to be sending a high energy electron beam in a transmission mode And then you're looking at electrons that have been inelastically scattered by some process. And this process can be anything from, say, a core loss process, such as an electronic absorption edge at quite high energy, or a bulk or a surface plasma. So you're just having to map the energy loss at the nanometer scale, and that tells you something about the behavior of this material in the optical range or in the electronic absorption edge range. The only slight downside with this technique is that it's a little bit more expensive than the UV vis. And for the kind of ranges we're looking at, we must add this extra sort of $1 million bit of kit on that, and that's an electron monochromator, where we want our electron energy spread to be very, very small to be looking at the optical region. So we're talking about several $1 million type instruments. A little bit of kind of deeper understanding of how this works. I don't want to spend too much time on that, but I always kind of get that question. So in the optical region, when we want to try to probe localized surface plasma on resonance, what we do is that we're going to be traveling an electron onto, say, a nanoparticle. That electron impinges on the sample and it carries its own field. That field interacts with the nanoparticle and actually does that one kick that I said a few slides ago. It will polarize that nanoparticle. And that polarization can then does create an induced field, and that works back at the electron that we are sending back in our column. And then you get a loss probability from that induced field interaction with the traveling electron. And you can calculate the loss probability based on that, and that's all related to your refractive index inside the particle, and then you basically get a high loss probability at the plasma on resonance because it's very highly polarizable at that point. And so this is what we're going to see when we do yields. And we've been doing a lot of yields and a lot of these maps, and I'll explain all what these maps mean through my talk. But along the way, and we worked a lot with silver and gold and aluminum and whatnot, but along the way we became very interested in magnesium, and that's really what I want to talk about today. So I'm going to start my talk by telling you about particle shapes, because magnesium is very unique from the rest of our typical metals in that it crystallizes in hexagonal close packed, not in face-centered cubic. So it's going to make completely different shapes. I'm then going to address head-on the issue of oxidation, because I always get this question: why don't they oxidize? Won't they blow up? And so on. So we're going to study what kind of oxidation we get. Then we're going to move on to really these plasmonic properties. And then I'm going to finish by telling you a little bit about the synthetic advances we made in decoration. All the papers I'm referring are here. We've really done this work over the past just about 2.5, 3 years. And there's a lot more to come. We have 4 more papers in the pipeline about magnesium. So this is all very, very exciting. We are interested in magnesium because it's abundant. It's over 2% of the Earth's crust. It's dirt cheap, and it's really biocompatible. You have about a 20th% of magnesium in your body. We're also obviously interested in it because it's plasmonic. And when you ask yourself what's a good plasmonic, well, you have to just go back to the tables of refractive indexes of the dielectric function, really. And you want to ask yourself, what is the real and the imaginary part of that dielectric function, and particularly that imaginary part, which encodes for your losses. So you want to look at a metal that has low losses in the region you're interested in having a resonance. And we all know that gold and copper have interband transitions, so they're not very good for plasmons in the blue and the UV. We all know that silver is really pretty good. But looking at magnesium, it's pretty encouraging to see that the losses are really pretty low across the UV, the visible, and the near IR. Another way to express that is to take the quality factor, okay? And that's basically a ratio of the real to imaginary, and the bigger that ratio is, the better you are. And I have this plot here of that ratio. And on top of this, I've put a little rainbow to show you the visible range, and I've dropped also the sunlight spectrum in the bottom. And my conclusion with this is basically that apart from silver, magnesium is really pretty good for sunlight matched plasmonics. And we should really consider it a real contender for whatever application we intend to do with plasmonics. And I'm not the only one that thinks that. A number of people have fabricated magnesium structures over the past about 5-6 years. And the typical behavior of plasmonic is observed. So if you make the little dots of this material closer or farther away from each other, well, they have different colors. But magnesium has had this appeal a bit different than the other metals, because it can do this magnesium to magnesium hydride back and forth reaction where the magnesium hydride is not plasmonic and the magnesium is plasmonic. So you can think of it as a turnable on or a sensor for hydrogen. There's also claims that magnesium is transient as a plasmonic, meaning that you could dissolve it in water and make your plasmonic material disappear. This is not quite what I want to do, but it can be useful. So there has been quite a bit of work, but I've always worked with colloidally synthesized particle, and I think they often are superior because they have a better crystallinity and they can be scaled. So this idea of fabrication didn't quite tempt me, but we did in the literature with my group, and we found out that the people who want to do hydrogen storage had a synthesis figured out for magnesium nanoparticles. They just hadn't really looked at their plasmonic properties. And so the synthesis is relatively simple. You take lithium and naphthalene that puts an electron on this electron carrier now. This wants to get rid of its electron, and it's mixed with a magnesium organometallic precursor in THF under argon atmosphere. A little bit of time, room temperature, get beautiful metallic magnesium nanoparticles, then quench that with isopropanol, and then get very, very nice crystalline particles. So these are examples of some of the reaction mixtures that we make. So you can see that they're highly crystalline, very flat facets, very nice particles of really quite bizarre shapes, I would say, which led us to scratch our heads and say, well, what underpins the shape in crystals? And I've had done a lot of work on that during my PhD, so it allowed me to dust off some of these concepts. And really, the idea here is that if you start with a crystal, you ask yourself, well, what is the crystal structure that will give you the orientation of the various crystallographic planes? Then you ask yourself, is the crystal twinned or not? And then you basically ask yourself, what is the relative surface energy or growth velocity of the different facets? And from that, you can get basically a crystal shape. This is encoded in what's called the Wolf construction, which is a construction to predict shape from surface energy. And in its very simple form, which is basically the single crystal form, you're basically just going to say that your h, which is the distance from the center of a crystal to a facet, is proportional, modulo proportionality constant, to the surface energy of that facet. And so if you have very low 100 surface energy in a cubic crystal, well, you're going to get a cube. And if you have low 111, you're going to get an octahedron. Well, that's fair enough. You can modify this to get basically a twinned Wolf construction, where you basically, very simple, just create two Wolf construction of two twins split by the twin plane, and you stick them together numerically to get basically the shape that you would expect for something that has a twin. We've done this a while ago and looked at 5-fold twins, for instance, where indeed you just assemble 5 units. And this is all for FCC materials. Again, quite a while ago with my very first PhD student in Cambridge, we coded this into a graphical user interface. This is all for cubic system, and where you can get, shapes easily by just entering a few parameters. And that's all been fine, but that doesn't answer our question about magnesium. And the deal is that it answers most questions about the most of the material that people are interested in, right? So if you look at in red here, this is basically all the materials we do nanotechnology with, or at least plasmonics, and copper, gold, silver, aluminum. It's all FCC. It's all the same deal. Magnesium is different, and a lot of the materials that are coming online for nanotechnology are also different. So we took on to analyze what we would get for wolf shapes on that. And the first thing to think of is what planes are going to be present and what planes are going to be low energy. So again, this is hexagonal, and in the hexagonal system, we use the redundant index I, so HKIL, where I is minus H plus K. That just helps with planes with the same number looking the same, but it's redundant. And so if we look at that, the basal plane, the 0001 plane, is close packed, so that's going to be very low energy. The side plane here in gray is going to be also pretty low energy. And then there's a number of inclined planes that I have named here that are also quite high density and low energy, and these are capable of being twin planes in the HCP systems. They are known to be twin planes in the HCP system. So we recoded our graphical user interface to now have not only cubic, but also hexagonal. This is all free on my website if you're interested in playing with this. We added a little touch of, well, not quite magic, but we use this a lot to this, in that we can export files for DDSCAT just based on this shape. So we export a shape file, and then we can run our electromagnetic simulation straight out of there. It's brilliant. But this allowed us to think what kind of shape would we get in magnesium, and here's the kind of stuff we get. So a single crystal hexagonal plate, nothing surprising. Then you start twinning, and you see these folded structures. And the first one we saw, well, we thought it looks like a tent. And then the next one is nearly 90 degrees and looked like a chair. And then we kind of went on, and the picnic team, and named the other ones taco and kite. And these are really rather unusual shapes when compared to the sort of cuboctahedron we get for FCC metals. And lo and behold, experimentally, this is what we get, right? So we see the tents, the chairs, the tacos, and the kites in our reaction mixture, and their proportion within the reaction mixture for the twin structures is actually related to the energy of this twin planes. So the twin planes in the 101 bar 1 is actually lower energy than the 112 bar 1, and there's just more of it. Disclaimer, we don't know how to control the twinning. We've not been able to do that. If you have ideas how to do that, I would be thrilled, but this is a little bit harder than for gold and silver due to the really pretty harsh reaction conditions. But really happy that we get a range of shapes, and we have the technology to do single particle spectroscopy, and so we don't fret at heterogeneity. So I'm not going to move to oxidation of these particles, because so far you basically seen, oh my God, she's making magnesium metal particles. Won't they oxidize? Won't they blow up? Isn't this too reactive? It sounds crazy. Well, I had my doubts when we started this about 4 years ago as well, but it turns out really they're not that bad. Okay, so take home message on this: yes, they oxidize, but it's self-limiting. And I'm going to show you a bit later that their reactivity is actually really useful when we try to decorate these particles with another metal. An easy way to show you that there's oxidation is a good old high resolution stem image. So this is an annular bright field stem. It looks kind of like a high resolution TM image. And basically what you see is the atomic packing here of the magnesium metal, which is hexagonal. And then that's coated by a thin layer of cubic MgO. As we expect, we can see that in the Fourier transforms of these images as well. Here we measure about a 5 nanometer layer. As you'll see in the next couple of slides, this thickness varies from particle to particle, and there are errors associated with a variety of the ways we measure this. Another way to check that it is indeed oxygen in there is to do an EDS map. Okay, so EDS is energy dispersive X-ray spectroscopy. It is an X-ray emission technique. And basically, if we park our beam on this particle, we would see magnesium, oxygen. This is on silicon nitride grid, so we see silicon and nitrogen as well. And then we can just basically map the magnesium signal or map the oxygen signal. And this is sort of what it looks like. If you look at a particle front on, we see magnesium, a bit of oxygen. You find one on the side. Well, you can also map that on the side. And if you want to deliberately map the center, well, you take the particle, you coat it with carbon, then you cut it with a focused ion beam, and now you really have a slice of that particle where you can more accurately measure that coating of oxygen. And we can do that, do a line scan through that. And well, it kind of depends on which particle you measure, to be completely honest. But roughly, you get a magnesium oxide of about 10 nanometer on a particle that's 40, 50 nanometer of magnesium metal thick. We can map on and on, right? The different sizes, the different shapes of particle. They all show the same behavior. They form a thin oxide layer around the structures. We can line scan on and on. Okay, I think I've made my message pretty clear, right? This magnesium oxide is roughly 10 nanometer. If we worry about this oxide, we can ask ourselves, well, how does it change the plasmonic properties of the structure? And unfortunately, we really can't ask ourselves that experimentally. We've not really been able to control that oxide thickness yet. But we can ask numerically, and this is discrete dipole approximation solving of Maxwell's equation. And what you're seeing is basically a pretty large particle, typical size that we make, with plasmon resonance in the visible and an increasing thickness of oxide layer without changing the thickness of the nanoparticle of the magnesium. And all you see here is really just a redshift. So we're pretty content that this oxide layer isn't damping the plasmon resonance, and that in fact it is probably not making a large dent in our possibilities of applications. Another way to check that this is still magnesium metal is to do what's called a bulk plasmon map. And magnesium and aluminum are really unique in that, is that they have a very sharp bulk plasmon absorption in the sort of 10 to 15 EV region. And so we can map that with eels, and it tells us this is metallic magnesium. Most metals have a bulk plasmon, but for aluminum and magnesium, they're very sharp, very easy to see. It's very, very convenient. And we can map exactly where the metal is and sort of look at that and look at our EDS maps and really understand what the shape of our plasmonic structure is. We have a number of projects now doing tomography with these maps and getting the real shape of the magnesium metal. We're pretty excited about that. And lastly, this oxide layer encapsulates this magnesium metal layer, and it stays like that. We can dry these particles in air, leave them on the bench for a while, do powder XRD, and we can still see the signature of magnesium metal in these structures. They're stable in organic solvent. The only thing they're really not stable in, as is water, because the magnesium form a water-soluble magnesium hydroxide and dissolves, which is not a bad thing for biomedical applications, for instance. Anyhow, I want to now move to, and I still have about 20 minutes. I want to now move to their plasmonic response. So I hope that so far I convinced you that they make really cool shapes and they're stable. But obviously the core here is that they are going to have to interact with light and create these strong electric fields around them. And again, we're going to be using this technique of electron energy loss spectroscopy, looking at inelastically scattered electrons. And depending on where we put our beam around this particle, well, we're going to see different response. And I've already mentioned that one of the responses is bulk plasmon, which can tell us where the magnesium metal is. But the other response is in this UV visible near IR range, where we actually see what I should write, localized surface plasmon modes, which we can also map with roughly nanometer resolution. And here's an example. So this is background subtracted on the left, okay, of if I put my beam here on one of these hexagonal nanoparticles, I see a number of bumps. Okay, I can fit these bumps to different peaks, and then I can extract a map. We can also do numerical. So this is EDDA. So this is solving Maxwell's equation, but for an incident electron beam. And the response match really pretty well because we use the correct amount of oxide on the substrate and so on and so forth. And so if we go ahead and map where these modes appear around our particle, we can get what people might say plasmon maps. Okay, they're loss probability distribution, and at different energies. So for instance, for here, you get a mode that is kind of symmetrical, looks like a donut. Then you have a mode that has high probability of loss around the tips, and then something that has high probability of loss around the edge and the center. And if you're an experimentalist like me, you will spend the rest of your life calling this the donut mode, or you call up to amazing theorists who can help you figure out just what the donut mode is. And these theorists are here in Cambridge, and it's just been wonderful. And so what they've been able to give us is the maps, the theoretical maps of loss, and I'm pretty convinced that these match really quite well with the loss we have. And then they can give us basically the phase of that electron oscillation, which from that we can diagnose which modes these are. And this is really a little bit more complicated than for simple Swifter. And so the first mode, well, it's not very surprising, is a dipole, and actually wherever you put your beam, so my electron beam is here for now, but wherever you put your beam around the particle, you'd excite this dipole, and so you get the donut shape. The second mode turns out, just your second mode starts to be complicated because it's actually a combination of two modes that are very close in energy. They're not degenerate, but they're close and they're both kind of broad, so they fall on top of each other, and there's kind of no way to tease them out. And that is the quadrupole here that I'm showing, and then a tip hexapole. The next mode at higher energy is actually an edge hexapole, which is not degenerate with the tip hexapole, as well as a radial breathing mode. So these modes are seen in all of the hexagonal particles that we've been looking at. Of course, at different size of particles, they're going to have different energy, but their distribution is essentially the same. We started looking at our other shaped particles. So this is a tent, for instance, and that little symbol I have here is just to say that it sits like this on the substrate, because a tent could sit as a tent or kind of as a chair on the substrate, and that actually leads to a little bit of symmetry breaking. In these modes, well, there's less symmetry in the particles, so we are going to be expecting less symmetry in the modes, so the modes become non-degenerate. So for instance, the dipole mode leads to a longitudinal dipole as well as a transverse dipole that are now not the same energy. The quadrupole is still there, and so on. So we are seeing a much richer set of modes as we are breaking the symmetry of these particles. And it obviously took us a while to figure out what was what, and it took us a lot of nanoparticles. So here you are, different particles of different size, slightly different aspect ratio, always give the same kind of story here. And then we looked at chairs and tents and other configurations, but really, bottom line is this is kind of the same story, and that story is summarized in this figure. Okay, bear with me for a second. Basically, in this kind of mode analysis, you can say that your mode energy is going to be related to the number of nodes you have along the width of your particle over the actual width of your particle, plus the number of nodes you have over the length of your particle over the length of your particle. So the more nodes you have, the higher energy the mode is, and the bigger the particle, the lower energy the mode is. Okay, pretty basic concept here. And so as we move from hexagon to longer folded particles such as tens, but the behavior is essentially the same for the other shapes, we basically again break our dipoles, and then they shift in energy. We break our quadrupoles, and our hexapoles actually turn into different modes as well. And then the relative energy of these different modes cross over as the particle size increases, essentially. On top of those shape effects, we have size effects. I don't want to spend too much time on that. This is just well known. It's just to show you that actually these are plasmonic structure behaving like every other plasmonic structure. And so if you take this graph, for instance, what I'm showing is the plasmon resonance for our first mode, second mode, third mode in hexagons, and showing you that as the size increase, the plasmon resonance decrease. But my favorite take-home message from this graph, though, is really the range that we can cover. These are hexagonal structures of magnesium, and you can see that they have plasmon resonance anywhere from 1.4 eV all the way to sort of 3.6, 3.7. So this really covers our visible range with strong plasmon resonances. We see the same thing for rods. Sometimes these particles form really elongated structures. They behave just like rods of silver, gold, copper, aluminum, and so on. Okay, just a whole bunch of longitudinal modes with a large number of nodes. So I hope that you've been convinced that these are plasmonic, that behave plasmonically, really just like our good old friends, silver and gold. One of the things that's different in magnesium, of course, is its reactivity, right? I always talked about the oxidation, which we used to worry about. We don't worry about as much. But another thing that's different is its electrochemical potential. And from that, we actually can drive chemistry that we really can't drive with gold. And I became interested in this business of sort of decorating particle with other particles when I was at Rice. And together with my colleague Naomi, we made these aluminum structures and decorated them with palladium. And she had shown in the lab that they were really good at catalysis. And then my lab took over a whole bunch of synthesis, and we did this whole bunch of the periodic table and showed that we could decorate with nearly as many metals as we want. Although here, what we did was to take pre-formed aluminum structures and then reduce with an extra reducing agent the other metals sort of on top, and kind of hopes that it sticks, and turns out it sticks. So that's great. With magnesium, we thought we'd do something slightly different, because the idea was maybe we could try to get a direct contact between the two metals without having an oxide layer between the two. So we thought we could try galvanic replacement. And the first hurdle here is that, well, if you Google galvanic replacement, you're going to see a ton of stuff, but it's all happening in water. So we ask ourselves, are we going to be able to do that in a non-aqueous solvent? And what kind of precursors can we use, and so on? So little side project, a couple months, try to do non-aqueous galvanic replacement. silver and gold, easy stuff. Turns out it works. Okay, so methanol, ethanol, IPA, it all works. You just have to find the right precursor of, in this case, gold, and that is soluble and works just fine. So we figured that out. We even managed to publish this, so that's great. So we need a non-aqueous solvent. That's fine. Another problem we were really worried about is that this magnesium oxide layer might prevent reaction, and we have seen that significantly in aluminum, where galvanic replacement of aluminum has eluded us for the longest time while we were at Rice. There's also a problem of a large lattice parameter mismatch. So we typically do galvanic replacement with metals that are miscible and that can basically epitaxially grow on top of each other. And, you know, for silver and gold, you get an alloy. This is great. This is just not going to happen with magnesium because of its different crystal structure. But to our rescue is the fact that magnesium is really far from noble and is actually very likely to drive a reaction in which the magnesium really wants to get rid of its electron and something else wants to take it. So a huge thermodynamic driving force. And of course it works, otherwise I wouldn't be talking about it, right? So first thing we tried, well, is the easy way out really, try with gold, because you'll see the plasma and resonance of gold appear if anything happens, and it does work, okay? So as we increase the amount of gold, we are seeing more and more gold particles, more and more of that sort of purple red color, and eventually if we put too much gold, everything crashes in solution. These decorations are indeed not an alloy and not a shell. They form small sort of peppered in decoration on the structures. This is not necessarily bad news, it's just a bit different. And again, as we put more gold, we see more of these decorations on the structure of our magnesium. This is not the same particle. Okay, these are different particles, but just with different amounts of gold. And you can really see that they have a really quite heterogeneous distribution of these gold structures. If you want to model that, it's a little complicated, of course, but if you are trying to sell this as a catalyst, you say, aha, well, I'm probing all the possible orientation and configuration of active sites, and you sort of get away with it, and that's great. We can map, of course, the elemental distribution around these, and we can see that there is gold, and the magnesium, the amount of magnesium actually decreases on these structures. It's obviously etched by this galvanic replacement by the gold. If we zoom in on that and ask ourselves whether there's an oxide layer, it turns out there is. So this idea that I was going to have the gold in intimate metallic contact with the magnesium actually really just didn't work. It seems that the magnesium oxide reforms at that interface. We are studying that a little bit more these days, but so far we still don't get a magnesium to metal contact with those, but it's not going to stop us. It never stopped us with aluminum, for instance. The plasmonic response of gold here, that's sort of 550, allows us to follow the reaction kinetics for this. We've done this with all the other metals I'll show, but I'm just going to show it for gold. And the bottom line is that this is really slow. Okay, so you're putting something with a huge thermodynamic driving force, and it takes it about 4 hours to do anything. And this is just telling us that the oxide layer is slowing things down significantly in this reaction. If magnesium metal was present and available, reactivity would be much, much greater. We've now done this with a whole slew of metal, right? Magnesium will basically give electron to most anything in the periodic table. So choose your precursor, give it a try, it works. So here's an example with silver. Again, more silver, more particles. We've done this with palladium as well, because palladium is a catalyst. We're now running catalysis reactions with that. We've done this with iron. We now have zinc and copper, and it just, it just works. The kinetics of each is slightly different, and the size and shape distribution of particle is slightly different, but overall, this does work. We're pretty sure this is a galvanic replacement mechanism by now, because we do see the magnesium etching out. We also are convinced that there's no other reducing agent in solution. The gold doesn't get reduced by anything else. This is ethanol at room temperature or isopropanol at room temperature, depending on our reaction. We don't get a reaction or reduction of our magnesium if you don't put the metal salt. The thermodynamics tells us it works. It works with basically any metal we want to try. And we can track actually where the magnesium goes from the kind of centrifugation pellet to the supernatant as the reaction goes. And that tells us that indeed it goes from magnesium metal to magnesium aqueous. So this is really what I had to say. I hope I'm on time. And so basically we learned about shapes, and magnesium makes unusual shape because it has a different crystal structure than a lot of the noble metals, but it doesn't have an unusual crystal structure when you look at the periodic table. So this should really help with the new type of metals that are made in nanoparticles these days. I hope I convinced you that the oxidation of magnesium is not a deal breaker to make magnesium an efficient plasmonic material. Hope I also convinced you that, hey, it is an efficient plasmonic material. And what I really like about this is that it does really span the UV, visible, and near IR. And it has very, very good properties everywhere where basically the sun shines. And that we can do quite a lot of chemistry. And the papers that I referred to are here. There are many more to come. And I do hope that at my talk at ACS Atlanta, I will have a lot of the new results that we're just about to publish. I'm going to acknowledge my group. Again, Jeremy, Christina, and Elizabeth are really the forefront of the magnesium effort in my group at the moment. And I will advertise that, if you are looking for a PhD or postdoc, it's always a good thing to shoot me an email if you think that, that this is the kind of work you might be interested in doing. So I'm going to stop here, go back to this slide, and I believe that we might have a few questions. So thank you very much for your attention.
Thanks, Emilie. That was great. And all new so far as the stuff that I've heard. So congratulations on that. As I mentioned to Professor Ringe at the beginning and also to the attendees, we're going to have Professor Rodrigo Noriega and also Professor Carlos Baiz. Rodrigo is from Utah and Carlos is from UT Austin. They're going to take turns moderating the questions. And I believe Professor Baiz is going to go first. So Carlos, go ahead.
Okay, great. So Professor Ring, thank you very much for your wonderful talk. There's a few questions from the audience. Actually, the first one is from Christy Landis. And the question is, how easy is it to integrate the magnesium nanomaterials with common semiconductor device materials?
Do you mean in the fabricated sense or in the colloidal sense?
I suppose either.
Yeah. So in the fabricated sense, it's moderately straightforward because you can evaporate magnesium and you can do all of the beautiful E-beam lithography and whatnot, as many people have done. And so in principle, not much harder than for any other metal in the fabricated sense. Same answer really for the colloidal, right? It is always a challenge to couple the silicon sort of semiconductor technology fabrication with sort of a vial of stuff in solution that you try to put in there. But I think that it is exactly the same challenge with magnesium as it is with any gold and silver and so on. These have a little bit of organic molecules on, just like gold and silver and so on. And so it's equally difficult, in my opinion. Yeah, not more, not less.
you. Our second question comes from Stefan Link, and the question is, what are the limiting steps to produce smaller magnesium nanoparticles to produce sharp plasma resonances that are ideal for SPR sensing, for example?
What are the limitations? Sorry, I missed
the limitations for making smaller magnesium nanoparticles.
Oh, smaller. Oh, we've absolutely cracked that nut. I've not shown these results, but basically by changing the overall concentration of everything in the solution and the reaction temperature, we can actually get structures down to about 50 nanometers. Which do have what you would expect as a plasmon resonance, which is sort of blue shifted, a little narrower, and so on and so forth. So no, there are no real limitations at the moment. I've just shown in my talk reaction from our, one type of syntheses, but yeah, if you stay tuned, you can get all the answers in our, newest and latest papers.
Thank you. And I just wanted to remind the audience again that please use the chat if you have any questions. The next question is the following. Does the ability to access different shapes in magnesium allow for easier localization of the LSPR modes in different parts of the nanoparticles and to tune the hot electron reactivity?
Yeah, absolutely. So if you look at the different shapes, so let's take this, right? If you look at one shape, you can have different types of modes at different energy. Now you can tune which energy this mode is at and where your electric field is going to end up. And then if you look at indeed different shapes, you are going to end up, with different mode localization, again at different energy. And that is true of the more pointy shapes like the kites and so on. So yes, we do expect a strong change in reactivity for these particles. We do expect a strong change in thermal response of these particles. We expect a strong change in refractive index sensitivity and so on when going from one mode to another, because that field localization is different. And look, I mean, this has been shown for a number of structures in gold and silver. The beauty here and the difference here is that the shapes we can access are really different. And funnily, and again, that's another paper we're writing at the moment, these are basically folded shapes that are sharp everywhere. And so we do get quite a bit of an electric field in that fold, as well as at the tips of these particles, depending on the mode. So yeah, it does give us a real knob to turn in terms of reactivity and of sensitivity. Yeah.
Thank you.
The next question is regarding the galvanic replacement process. And it is, does the galvanic replacement rate follow some trend with oxide layer thickness that you would expect, for example, from tunneling?
Yeah. So if I understand the question correctly, is if you make your oxide layer thicker, do you see a slower reaction? Mm-hmm. Yeah, I would love to be able to answer this question from experimental data. Unfortunately, we really don't have a good way to control this oxide layer. Deliberately trying to oxidize the particles is really quite uncontrolled. And so we don't have kinetic data based on that. I would definitely expect that you would get basically slower kinetics with thicker oxide, but I don't have data to show that. That's a really good question, and the day we manage to control the oxide layer, we're definitely trying that.
Thank you.
And the last question from the audience is the following: given the multipolar resonances that you get with the shapes, what do you gain or lose by fabricating coupled nanostructures to create coupled modes and create hotspots?
Yeah, I mean, in these structures, you can actually get a hotspot of much higher electric field by coupling two nanoparticles rather than relying on the intrinsic higher order modes in these structures. That also would enable you to maneuver the plasmon resonance so that that coupled plasmon is likely to be at quite higher, higher wavelengths, a lower energy than an uncoupled mode. I think there would be something to gain in there. Again, this is a little bit tricky to make because these are not fabricated structures. If you want to make a coupled structure, a bow tie or something, if you fabricate, well, that's relatively simple. If you rely on a solution of stuff and you deposit that on the grid and then you see how the particles land, well, then it's a little bit heterogeneous. It's great for studying the stuff, but in terms of an application, it's a little bit less reproducible. But yeah, hotspots would be created. Again, someone can ask what would be the effect of the oxide layer, which I could say I don't know experimentally, but I can very well calculate. Indeed. Yeah.
Thank you.
Emilie, that was outstanding. It's a great talk. And definitely well worthy of our first award talk of this summer session, and certainly well deserving of the JPCC Lectureship Award. So congratulations and very much well deserved.
Thank you. It's a wonderful honor.
Well deserved. And for now, what we